Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series.
It is so wonderful to be back here with you today.
Today, we are exploring liquid biopsies, the revolution in non-invasive cancer monitoring. And I have to say, looking at the massive stack of research we have on the table today, I mean, we've got systematic reviews from 2024 and 2025. We have the Vanguard trial data and even papers on veterinary oncology.
Right, the dog studies.
Yeah, exactly, the dog studies. It really feels less like a standard medical update and more like, I don't know, science fiction that is somehow becoming reality right now.
It really does. It feels entirely futuristic.
If you just imagine detecting cancer, not by cutting into the body, not by waiting for some lump to appear, but simply by drawing a standard vial of blood.
We are truly standing at a precipice in oncology right now, because this isn't just some incremental improvement. You know, it's not a slightly sharper scalpel or a chemotherapy pill with fewer side effects. We're witnessing a fundamental paradigm shift here.
Which is exactly what we want to convey to you, the listener, today.
Exactly. We are moving from reactive medicine, which is basically waiting for the disaster to happen, to proactive molecular surveillance.
And that distinction, that reactive versus proactive idea, that is really the core mission of our discussion today, right? Because historically, if you think about it, cancer treatment has been almost entirely reactive.
Precisely. Just think about the standard of care for the last 50 years or so. We wait for symptoms.
You feel a lump.
Right. You feel a lump, or you have a persistent cough that just won't go away, or maybe, if you are incredibly lucky, a doctor spots a weird shadow on a routine CT scan. But by the time a tumor is actually large enough to be seen by the naked eye or a scanner, it already contains billions of cells. Billions. It has established its own blood supply. It has likely been growing there in the dark for years.
So basically, by the time we actually see it, the enemy is already completely entrenched.
Entrenched and fortified. And this new liquid biopsy technology offers the potential to shift that timeline dramatically. The hook that really grabs people, the thing that makes this so fascinating, is the idea that our blood is essentially this massive biological highway.
A highway carrying secret messages?
Yes, secret messages from literally every tissue in our body. And if there's a tumor hiding somewhere, even just a tiny microscopic cluster of cells, it is leaking evidence into that bloodstream.
The sources call them ghosts of tumors past, present, or future.
Which is such a haunting image, isn't it?
Yeah.
But it's biologically accurate.
It is haunting. So let's really unpack this for you all today, because we have a massive amount of ground to cover. We need to understand the foundations first, like what exactly are we hunting for in the blood?
And then we need to look at the active debates. Because as we learned from poring over these papers, the science is really messy and the biology is incredibly noisy.
Super noisy. And finally, we'll look at the frontiers, things like AI, fragmentomics, and what all of this ultimately means for society, economics, and ethics.
Sounds like a solid roadmap.
Let's start with the basics, the foundations. Now, most people know what a traditional biopsy is. You go to the hospital, they numb you up, they take a large needle or a scalpel, and they physically cut out a piece of tissue.
It's invasive, it hurts, and it obviously carries risk for the patient.
Right. So how does the liquid version actually compare, other than just being, way easier on the person getting the test?
Well, the easier part is obviously a huge win for patient comfort, but the scientific advantage is actually about information quality.
Information quality.
Yeah, so think of a solid tissue biopsy as a photograph, a snapshot. You stick a needle into a tumor, you pull out some cells, and you analyze them under a microscope. That tells you what is happening in that specific, tiny millimeter of tissue at that exact second in time.
But a tumor isn't just a uniform, identical blob of jelly, right?
Oh, far from it. Tumors are incredibly heterogeneous. They are these chaotic, evolving ecosystems. The cells on the left side of a tumor might have completely different genetic mutations than the cells on the right side.
So they mutate differently depending on where they are.
Exactly. And if the cancer has spread, say it has metastasized to the liver or the brain, those secondary tumors might have evolved to be genetically distinct from the original primary tumor.
So if you just biopsy the main tumor in the lung, you might completely miss the mutation that makes the liver metastasis so dangerous.
You hit the nail on the head. We call this spatial bias. You are treating the patient based on a tiny sample that doesn't actually represent the whole war going on in their body.
That sounds like a massive blind spot.
It is. Now contrast that with a liquid biopsy. Because your blood circulates through the entire body, it washes over the primary tumor, it washes over the metastases, the lymph nodes, everywhere. So it captures a composite picture.
It's not a snapshot anymore.
Right, it's not a snapshot. It's a global summary of the entire disease burden.
It's like the difference between looking at one room in a house versus looking at the master blueprints for the whole building.
That is a perfect analogy.
But what are we actually looking for in that blood? In the research papers, they constantly refer to the big three analytes.
Yes, the big three. These are the biological materials we are actually isolating from the blood plasma. They are circulating tumor cells, which we call CTCs, then circulating tumor DNA, or ctDNA, and finally exosomes.
Okay, let's break these down for everyone so we have a clear picture. First up, the pioneers of this tech, the circulating tumor cells, or CTCs.
Right, so CTCs were actually the first to be discovered way back in the 19th century, believe it or not. But they only became clinically relevant in the 1990s. These are intact, whole cancer cells that have physically broken off from the primary tumor and entered the bloodstream.
I saw a great analogy in one of the systematic reviews describing these as scouts.
It fits perfectly.
Yeah.
Imagine an invading army, which is the tumor, and it's trying to expand its territory. It sends out scouts to find new places to colonize. Those scouts are the CTCs.
So they are actively looking for a new home.
Yes, and if they survive the turbulence of the bloodstream and manage to land at a hospitable organ, that is exactly how metastasis starts.
So if you draw blood and find a CTC, that is basically absolute proof that the cancer is on the move.
Yes, it is. But catching them is an absolute nightmare
Why is that?
because they are incredibly rare. In a standard vial of blood, you have billions of red blood cells and millions of white blood cells. You might have one single CTC in that entire tube, maybe 5. It is literally finding a needle in a haystack.
Wow, one cell out of billions. But because it's a whole cell, if you do manage to catch it, you can do a lot with it, right?
That's the major upside. Since the cell is totally intact, you can grow it in a lab. You can test different chemotherapy drugs on it to see what works. You can sequence its entire genome. It gives you the absolute most data. But as I said, it is the hardest to find.
Okay, so CTCs are the scouts, rare whole cells. Next up is the one that really seems to be dominating the headlines lately, the ctDNA, or circulating tumor DNA.
This one is currently the absolute superstar of the field. While CTCs are whole, living cells, ctDNA is just fragments. It's tiny pieces of genetic code floating freely in the blood plasma.
But wait, why is the tumor dumping its DNA into the blood? I always thought DNA was supposed to stay locked safely inside the cell nucleus.
Under normal, healthy circumstances, yes, it absolutely should. But tumors are messy. They grow so incredibly fast that they often outstrip their own blood supply, or the body's immune system manages to attack them.
Which causes them to die off.
Exactly. This causes massive amounts of cell death, specifically apoptosis and necrosis. And when those tumor cells explode or wither away, they just spill all their internal contents everywhere.
So it's essentially just cellular trash.
In a way, yes, it's the tumor's garbage. But for oncologists, it's absolute treasure. By sequencing that trash, we can read the tumor's specific genetic code, its unique mutations, without ever actually touching the tumor itself. And unlike the whole cells, these DNA fragments are much more abundant.
But abundant is pretty relative here, right?
Very relative.
Yeah.
We are still talking about a tiny, tiny fraction. Remember, your normal healthy cells are also dying and shedding their DNA into your blood every single day.
Just from normal cell turnover.
Right. That normal background noise is called cell-free DNA or cfDNA. The actual tumor DNA, the ctDNA, is just a minuscule percentage of that total pool. Sometimes that's less than 0.1%.
So we're basically rummaging through the body's massive recycling bin, trying to distinguish the trash from a cancer cell from the perfectly normal trash of a healthy blood cell.
Precisely. Which naturally brings us to the third analyte in the big three, the exosomes. These are really the new frontier in liquid biopsies.
These honestly sounded the most sci-fi to me when I was reading the papers.
They are completely fascinating. Exosomes are a type of extracellular vesicle. Think of them as these tiny nano-sized bubbles, maybe about 30 to 150 nanometers wide.
So they are incredibly small.
Minuscule. But unlike the ctDNA, which is just passive debris from a dead, exploded cell, exosomes are often actively secreted by living cancer cells.
Wait, so this isn't trash at all?
No, not at all. I like to think of them as cargo ships or maybe messages in a bottle. The tumor actively packs these little bubbles with specific proteins, lipids, and even RNA and sends them out into the body on purpose.
Sending them where, exactly, and to do what?
That is the scary part. We've seen evidence in the research that tumors send out these exosomes to terraform distant organs.
Terraform, like preparing a planet.
Exactly like that. They arrive at the liver or the lungs, and they prepare the soil, so to speak, making that new tissue more receptive to a future metastasis.
That is deeply unsettling.
It is, but for diagnostics, the beauty of exosomes is that they are highly protective. DNA that is just floating freely in the blood degrades very quickly. But the RNA hidden inside an exosome is protected by a tough lipid shell. It acts like a time capsule.
That is incredible. Okay, so just to recap for you listening, we have the scouts, which are the CTCs, we have the trash, the ctDNA, and we have the cargo ships, the exosomes.
It's spot on.
But knowing these things exist in the blood is one thing. Actually finding them reliably enough to base a real human being's cancer diagnosis on it, that just seems like an insurmountable engineering challenge.
It is the absolute definition of a needle in a haystack problem. And the technological tool that actually solves it, or at least is currently solving it, is NGS, or next-generation sequencing.
We hear NGS thrown around constantly in these biotech papers. What does it actually mean in plain English for this context?
Well, in the old days, genetic sequencing was linear. You had to read one strand of DNA at a time. It was incredibly slow. NGS allows us to read millions of DNA strands simultaneously.
Millions at once.
Yes. Imagine you're in a massive library. Old sequencing was like picking up one single book, reading it cover to cover, putting it down, and then picking up the next book. NGS is like taking a high-resolution drone photo of all the open books in the entire library at the exact same time.
Okay, so you can scan the entire bloodstream's worth of DNA in one massive go. But you mentioned the needle in a haystack problem earlier. If the tumor DNA is only 0.1% of the sample, and this amazing sequencing machine makes even a tiny mistake.
You've hit on the critical flaw of early NGS. Every single sequencing machine has a baseline error rate. If the machine has a 1% error rate and you are desperately looking for a 0.1% signal, you are flying blind.
Because the machine's own noise completely drowns out the actual cancer signal.
Exactly. So how do we fix that?
Yeah, how do they fix it? Because that seems like a physics limitation.
Two brilliant biochemical innovations. The first is UMIs, which stands for Unique Molecular Identifiers.
Right, the UMIs.
Think of these as tiny molecular barcodes. Before we even put the sample into the sequencing machine, we chemically attach a totally unique barcode to every single DNA fragment in that tube of blood.
Okay, so it's like individually tagging every single piece of hay in the haystack before you even start looking for the needle.
Exactly. Then, to read the DNA, the machine has to make multiple copies of it. If we look at the results and we see mutation in only some of the copies that have a specific barcode, we know it's just a machine error, a typo made during the copying process.
Oh, I see.
But if we see that same mutation in every single copy that carries that exact original barcode, then we mathematically know the mutation was present in the original molecule drawn from the patient's arm. It allows us to completely filter out the machine noise.
That is incredibly clever. It's basically built-in error correction for biology.
It really is.
Yeah.
And the second major innovation is ddPCR, or digital droplet PCR.
Digital droplet.
Yes. Instead of mixing the whole blood sample in one big test tube, we use oil to partition the liquid sample into millions of microscopic individual droplets.
Like shaking up oil and vinegar?
Exactly like that. Some of those tiny droplets will contain a DNA fragment, and some will be completely empty. We then run the chemical reaction in each droplet individually.
So you separate them all out.
Right. It turns a chaotic, messy analog mixture into a very simple binary digital count, positive or negative. It gives us absolute, precise quantification of how many mutant fragments are there.
It's truly amazing how much pure physics and engineering goes into just reading the biological code.
It takes a village of different scientific disciplines, really.
So we have the biology down, we have the tech down, but let's ground this for everyone listening. Is this actually helping patients right now in hospitals? Or is this still just really cool stuff happening in a research lab?
Oh, it is absolutely shifting into the standard of care right now, specifically in three main areas. The first, and definitely the most established area, is genotyping.
Genotyping. That's matching the specific patient to the specific drug, right?
Yes. Let's take lung cancer as the prime example here. There are some incredible new drugs that target very specific genetic mutations, like the EGFR mutation.
Right.
If you have that specific EGFR mutation, you can take a targeted pill and it can literally melt the tumor away with minimal side effects compared to chemo. But to know if you actually have that mutation, the doctor needs to test the tissue.
But lung cancer patients are often very, very sick. Their lungs are already severely compromised. Sticking a large needle into their lung just to get a sample is inherently risky.
Exactly. It can easily cause a collapsed lung, which is a life-threatening complication.
Huh?
Or sometimes the tumor is just hiding in a spot near the heart that the surgeon simply cannot safely reach.
So what did they do before liquid biopsies?
In the past, if we couldn't safely get that tissue, we just had to guess, or we had to give them harsh, generic chemotherapy and hope for the best.
That is brutal.
It was. Now, we can just draw a vial of blood, find the EGFR mutation floating in the ctDNA, and immediately prescribe that targeted life-saving drug without ever putting a needle near the patient's lung. That is saving lives and sparing severe trauma today.
That is incredible. So that's the diagnostic side of things. What about monitoring the cancer once treatment has started?
That's the second major application, treatment response. Right now, if you are on standard chemotherapy, how do doctors know if the drug is actually working?
Well, you just wait, right? You do the chemo infusions for a few months, and then eventually you do another CT scan and you cross your fingers and see if the blob got any smaller.
Right. You wait 2 or maybe 3 agonizing months. That is a very long time to be pumping a highly toxic drug into your body if it turns out it isn't actually hurting the cancer.
Yeah, it's lost time.
The liquid biopsy blood test completely changes that clock. Because ctDNA has a very short half-life, meaning it clears out of the bloodstream in just a couple of hours, it gives you a near real-time readout of what the tumor is doing.
Real-time monitoring.
Yes. If you start a new chemo drug on a Monday, and by Thursday you do a blood test and the ctDNA levels have dropped by 90%, you know for a fact the tumor cells are dying.
And what if those ctDNA levels actually go up?
Then you know the tumor is resisting the drug, and you need to switch treatment strategies immediately. You don't waste 3 months poisoning a patient with a drug that isn't working.
That is a game changer for patient quality of life.
It is. In fact, one of the review papers from 2024 mentions that liquid biopsies can show tumor growth months, and sometimes up to a full year, before that growth ever becomes physically visible on a CT scan. That concept is called lead time.
A whole year. That is practically a lifetime in cancer treatment. It's the difference between fighting a tiny skirmish and fighting a full-blown entrenched war.
Which naturally leads us to the third clinical application, MRD, or minimal residual disease.
MRD.
This is specifically for patients who've already had their tumor surgically removed. The surgeon comes out to the waiting room and says the words everyone wants to hear, "We got it all."
The phrase everyone prays for.
Exactly. But visually, with the naked eye, the surgeon can only see what they can see. Microscopic cancer cells might still remain hidden in the tissue margins or the blood.
The invisible leftovers.
Right. Currently, because of that fear, we often give patients months of post-surgery chemotherapy just in case there are stray cells.
Which is awful to go through if you don't actually need it.
It is unnecessary toxicity for a lot of people who were already cured by the surgery alone. But for others, that standard round of chemo might actually not be aggressive enough.
So MRD testing checks for those leftovers in the blood.
Exactly. If you physically remove the tumor and the ctDNA levels in the blood drop to absolute 0 and stay there, you might be totally cured. No chemo needed. But if the ctDNA is still present in the blood, even at incredibly tiny levels weeks after the surgery, we know definitively that the cancer is still hiding somewhere in the body, and recurrence is highly likely.
So you can hit them with the heavy drugs right away.
Right. It allows us to completely personalize the post-surgery treatment plan based on real molecular evidence, not just statistical guessing.
It sounds perfect. Honestly, listening to this, it sounds like the magic bullet we've been waiting decades for. But I know science, there's always a but.
There's always a but. Science is never that simple. For all this incredible promise, there are massive biological hurdles and very active debates that are keeping researchers up late at night.
Let's get right into the controversy then, the active debate section of our talk. What is the absolute biggest headache for scientists in this field right now?
The biggest headache by far has a name, and it's called CHIP.
CHIP, clonal hematopoiesis of indeterminate potential. That is quite a mouthful.
It really is, but the underlying concept is vital to understand. Here's the massive problem. As we age, our normal, perfectly healthy cells naturally accumulate genetic mutations. It's just an unavoidable part of being alive.
Like wear and tear.
Exactly. Damage from the sun, cosmic rays, natural DNA replication errors over decades. Our white blood cells, the immune cells that are constantly being manufactured in our bone marrow, they accumulate mutations in specific genes like P53 or KRAS.
Wait a minute. P53 and KRAS, those are the famous cancer-driving genes, aren't they?
They absolutely are. But in this specific case, these older white blood cells aren't actually cancerous. They still function totally normally. They just happen to have a random typo in their genetic code because the person is 60 or 70 years old.
Oh, I see the problem immediately. If you sequence the blood looking for cancer and you see a P53 mutation.
Exactly. The machine rings the alarm bell. But is that P53 mutation coming from a hidden, dangerous lung tumor? Or is it just coming from a totally normal, aging white blood cell floating by? This is what we call biological noise.
It's a massive false alarm. A liquid biopsy test might scream cancer when the reality of the situation is just called aging.
And this is extremely common. In older patient populations, a huge percentage of the mutations we find floating in the blood are actually just this CHIP phenomenon, not cancer at all. If we don't figure out a way to account for this, we risk misdiagnosing thousands of healthy people and terrifying them.
So how do we actually filter that out? If the noise looks exactly identical to the signal, what do we do?
The current best solution is quite expensive, but it is effective. It's called matched sequencing.
Matched sequencing.
Yes. When we take that initial tube of blood from the patient, we put it in a centrifuge and spin it down to separate the layers. We took the clear plasma at the top, which contains the free-floating tumor DNA, but we also extract what's called the buffy coat, which is a middle layer that contains all the intact white blood cells.
Okay.
And then we run the NGS sequencing on both of them separately.
Ah, so you compare the two results side by side.
Right. If we see a dangerous mutation in the plasma, NAD, we see that exact same mutation inside the white blood cells, we know it's just CHIP. It's just normal aging, so we safely ignore it.
It cancels out.
Exactly. But if the mutation is only found in the free-floating plasma but not in the patient's white blood cells, then we know it's coming from somewhere else in the body, which is highly likely to be a hidden tumor.
That makes perfect logical sense. But having to sequence everything twice? That completely doubles the laboratory work.
It doubles the work, it doubles the time, and it doubles the cost.
Yeah.
But right now, it is absolutely necessary to guarantee accuracy.
There's another big debate I saw highlighted in the research notes, and it's this concept of discordance. We touched on this briefly earlier, but it's the idea that the liquid biopsy result and the traditional tissue biopsy result just flat out don't match each other.
This happens far more frequently than you might think. You do a traditional needle biopsy on a lung tumor, send it to the lab, and the report says it has mutation A. You do the new liquid blood test on the exact same day, and the blood report says it has mutation B.
And historically, the medical community trusts the solid tissue, right? The tissue biopsy has always been the gold standard.
Yes, for decades. If the blood test didn't perfectly match the tissue test, the immediate assumption was that the blood test was flawed, a false positive. But the entire medical perspective on this is currently shifting.
Shifting how?
We are starting to realize that the solid tissue might actually be the one that's wrong, or at least woefully incomplete, because of that spatial bias we discussed at the very beginning.
Because the needle only grabbed one tiny piece of the tumor.
Right. The blood test is seeing the whole massive picture of every cancer cell in the body. The tissue needle is just seeing one isolated pixel. So the scientific community is moving away from asking, is the blood test accurate compared to the tissue? And instead asking, does the blood test give us clinically useful information that the tissue biopsy completely missed?
It's a total reframe of how we view diagnostic truth. But beyond the deep biology, there's also some really unsexy, purely practical stuff that can totally mess these tests up, right? Like the literal plastic tubes the blood goes into.
Yes, the pre-analytical variability. It sounds incredibly boring, but it is critical to get right. Imagine you draw a vial of blood from a patient in a small rural health clinic. That little plastic tube contains millions of healthy white blood cells.
Right.
If that tube sits on the dashboard of a courier truck in the hot summer sun for 4 hours before finally getting to the main laboratory, those white blood cells are going to start to stress out.
And they die.
They die, and their cell membranes physically burst open.
And when they burst, they dump all of their normal, healthy DNA straight into the plasma.
Exactly. They completely flood the sample with normal DNA. Remember, we are already looking for a microscopic needle in a massive haystack. If you let those white cells burst in transit, you are effectively dumping a ton of extra hay onto the pile before the scientists even start looking. You drown out the faint tumor signal entirely.
So the pure logistics matter immensely. The temperature, the handling, the specific type of chemical preservative inside the tube.
Hugely. And currently, across the globe, there is a severe lack of standardization. Different hospitals use entirely different brands of tubes. They use different spinning speeds in the centrifuge, different chemical isolation kits.
Which means the data isn't comparable.
Exactly. It makes it very hard to compare clinical studies or to ensure that a patient gets the exact same quality of test in Kansas as they do at a premier hospital in Boston. We need universal protocols desperately.
One last controversy in this section before we move to the future tech, the concept of overdiagnosis. Now, this one feels more deeply ethical than purely technical.
This is the massive ethical gray zone we are walking into. As our sequencing machines get more and more sensitive, to the point where they can detect literally one single mutated molecule in a bucket of blood, we are inevitably going to find cancers that are microscopic.
But wait, isn't that the entire goal of all this? Catch it as early as humanly possible.
Usually, yes. That is the mantra. But not all cancers are actually killers. Some tumor cells are what we call indolent,
Meaning they are slow.
meaning they grow so incredibly slowly that they would never actually cause a symptom or harm the patient in their natural lifetime. If we find a tiny indolent cluster of cancer cells in an 85-year-old man, a cluster that would take 20 full years to grow into a real problem, and we panic and treat it with aggressive surgery or toxic chemo, are we actually helping that man? Or are we just causing severe harm and side effects for no reason?
Wow. We're basically creating a patient out of someone who was fine.
We are creating what sociologists call a patient in waiting, someone who walks around every single day knowing they have a definitive molecular signal of cancer in their blood, but they have no visible tumor to scan and nothing to physically treat.
The psychological weight of that must be crushing.
The psychological impact of that molecular illness is profound, and we don't fully understand it yet. Do we treat them blindly? Do we just wait and scan them every month? We honestly don't have the medical guidelines for that scenario yet.
That is heavy. It's like knowing a storm is definitely coming, but not knowing if it's going to be a devastating hurricane or just a light drizzle.
And not even knowing if the storm will actually hit land before you pass away from old age.
Okay, so we've covered the amazing basics and the terrifying problems. Now let's talk about the solutions, the frontier section. What is coming down the research pipeline right now that might actually solve these complex issues?
The entire future of this field revolves around one word: integration. We are moving far beyond just looking at DNA mutations in isolation. We are fully entering the era of multiomics.
Multiomics. Please break that buzzword down for us.
It boils down to simple biology. Genetics, the DNA, is really just the blueprint of the house. It tells you what could potentially happen if the plans are followed. But transcriptomics, which is the RNA, and proteomics, which are the proteins, they tell you what is actually happening functionally on the construction site.
So instead of just looking for a tiny typo in the instruction manual, we're actually looking at what the biological factory is physically building in real time.
Exactly. And when you combine all of these different layers together, the diagnostic sensitivity just skyrockets.
We have an example of that working.
Yes. One of the recent studies showed that for detecting early ovarian cancer, looking for ctDNA mutations alone was just okay, maybe catching 50%. But when they combined the DNA test with looking for specific protein markers, like the CA125 protein, the accurate detection rate jumped significantly higher.
Because you have multiple lines of evidence.
Right. It's like having 3 completely different independent witnesses at a crime scene instead of just relying on one blurry photograph.
Another massive frontier I saw in the notes was something called fragmentomics. And I just have to say, I love that word. It sounds like a superpower from a comic book.
It really does. And it is honestly one of the most elegant concepts in the entire field right now. Until very recently, all our sequencing focused purely on the specific sequence of the DNA. We were looking at the literal letters, the A, C, T, and G. We were looking for spelling typos.
Right, the mutations we talked about.
Exactly.
Yeah.
But fragmentomics doesn't care about the letters at all. It looks at the physical shape and the length of the DNA pieces floating in the blood.
The physical shape. How does the shape of a tiny molecule help you find cancer?
It turns out that DNA isn't just a loose, floppy string inside the nucleus. To fit inside the cell, it is tightly wrapped around these tiny protein spools called nucleosomes. It's incredibly organized.
Okay.
And different cell types have very different winding patterns. A liver cell winds its DNA onto the spools differently than a lung cell does, because a liver cell needs to keep different specific genes exposed and accessible for its daily jobs.
Okay, I follow the spools concept.
So when a cell naturally dies and its membrane bursts open, the enzymes in the blood that chop up the DNA usually only cut in the exposed, fragile parts between those protein spools.
Ah, so the spools protect certain lengths of it.
Exactly. And because cancer cells are chaotic and have very messy, abnormal winding patterns compared to healthy cells, Their DNA gets chopped into very different lengths than healthy DNA.
So the physical length of the fragment acts as a unique fingerprint.
Yes. Cancer DNA fragments found in the blood are often notably shorter than healthy fragments. Or they might have very different end motifs, which are the specific letters right at the exact cut point.
That is wild.
And this approach is huge for two major reasons. Number one, it's potentially much cheaper because you don't need to do incredibly deep, expensive sequencing to find one rare spelling typo. You just use software to look at the overall pattern of fragment lengths.
Which is easier computationally.
Right. And number two, the Holy Grail, it can potentially tell you the tissue of origin.
Wait, explain that part, the tissue of origin.
Because the physical packing of the DNA on those spools is highly specific to the cell type, the fragmentation pattern carries a hidden signature of exactly where in the body it came from.
Oh, wow.
So if you find weird cancer DNA fragments in the blood, the fragmentomics software can look at the lengths and tell you this pattern means the cancer is specifically coming from the pancreas, rather than just vaguely saying there is cancer somewhere in this body.
That completely solves the nightmare scenario of getting a positive blood test but having absolutely no idea where to aim the MRI scanner.
Precisely. That is the exact problem the DL5 platform you read about is trying to solve. DL5I is analyzing what they call the fragmentum.
But doing all of this, the multi-omics, measuring millions of fragment lengths, reading billions of letters, this has to create an unfathomable amount of raw data.
It creates exabyte scale data. It is far, far beyond what any human pathologist could ever hope to look at on a glass slide.
So naturally, enter the AI revolution.
Inevitably. We absolutely need advanced machine learning algorithms to spot these incredibly subtle patterns in the noise. An AI can instantly look at the DNA mutation, the protein level, the fragment length, the patient's age, and their medical history, and integrate all those thousands of variables to output a single actionable risk score.
And there's also this concept I saw called radiogenomics, which is merging the liquid biopsy data with traditional radiology scans.
Yes, that is a fascinating frontier. An AI analyzes the patient's CT scan image, looking for microscopic textures and pixel patterns that the human eye physically cannot see, and then it combines that image analysis with the genetic liquid biopsy data.
So it blends the physical image with the molecular data.
Exactly. And the combination of the two is vastly more powerful and predictive than either one alone. It's the ultimate convergence of digital imaging and biological data.
We also can't talk about frontiers without bringing up the Vanguard study. This seems to be a massively pivotal moment for what they call MCEDs, or multi-cancer early detection tests.
MCEDs are basically the holy grail of oncology right now. The goal is one single blood test that you take at your yearly physical to screen for 50 different types of cancer simultaneously.
50 types?
Yes. Because right now, most deadly cancers, like pancreatic, ovarian, or gastric cancer, they have absolutely no routine screening tests.
You just find them when they start hurting.
Exactly, when it's usually too late. MCEDs aim to change that entirely. The Vanguard study is so fascinating because it's not just testing the biology, it's testing the real-world implementation. It's a massive, randomized clinical trial where tens of thousands of patients get the blood test. But for half of them, the results are blinded.
Blinded? Why on earth would you blind the results? That seems almost cruel. We tested your blood for cancer, but we just aren't going to tell you the results.
It sounds harsh, but it's the only way to be scientifically rigorous. They need to compare the long-term outcomes of the people who act on the blood test results versus the control group who just receive standard medical care.
To see if it actually makes a difference in survival.
Exactly. They have to prove that rolling out this test actually reduces late-stage cancer diagnoses across the entire population, without the statistical bias of everyone knowing they've been tested. They're also closely tracking the psychological impact, answering the question, does a false positive result ruin a patient's quality of life through sheer anxiety?
That is the ultimate proof the medical community needs, because if we're going to roll this out to millions of healthy people, we had better be absolutely sure the test helps more people than it hurts.
Exactly. And speaking of helping entirely different populations, there is a truly fascinating crossover happening right now with our four-legged friends.
Yes. Veterinary oncology, I was so surprised by this in the stack, but I love this part.
We call this paradigm One Health. It turns out dogs develop spontaneous, naturally occurring cancers that are biologically very similar to human cancers.
Like what kinds?
Lymphoma, osteosarcoma, breast cancer. And importantly, dogs share our exact environments. They live in our houses, they breathe the exact same air, they drink the same tap water.
So they act as biological sentinels for us.
They absolutely do. Advanced liquid biopsy tools are currently being tested in pet dogs to actually accelerate human research. Because dogs naturally age faster than humans, running clinical trials in dogs can give us vital answers about whether a liquid biopsy accurately predicts cancer recurrence in just 2 years, instead of waiting 10 years for a human trial to finish.
So Fido gets a cutting-edge blood test, gets much better cancer treatment, and that exact same data helps speed up FDA approval for human tests.
Exactly. It's a beautiful win-win scenario for both species.
It really is a powerful reminder that we are all biologically connected. Okay, so we've thoroughly covered the underlying tech, the complex science, the debates, the animals. Now let's look at the final piece of the puzzle, the implications section. What does all of this actually mean for you and me, for everyday society?
When you zoom out, the societal impact really comes down to 3 massive pillars: economics, access, and ethics.
Let's tackle economics first. These tests sound phenomenally expensive. You're talking about next-generation sequencing, advanced bioinformatics, supercomputers running AI. That is definitely not a cheap $10 lab test.
No, it certainly isn't. Running these multi-omics panels can cost several thousands of dollars per test currently. And because of that, massive insurance companies are understandably very hesitant to pay for them. They are demanding rock-solid proof of what they call clinical utility.
Okay, what's the difference between clinical utility and clinical validity? Because those sound like the exact same thing.
They sound similar, but in the medical billing world, they are completely different. Clinical validity simply means, does the chemistry work? Does the test accurately find the cancer DNA in the blood?
Right.
But clinical utility means, does finding the cancer actually improve the patient's life, extend their survival, or ultimately save the healthcare system money?
Ah, the bottom line.
Right. If you invent a brilliant test that perfectly finds a rare cancer, but there is absolutely no known drug to treat that cancer, or you find it but the patient still dies at the exact same time they would have anyway, the insurance company simply asks, why should we pay $5,000 for this information?
That is incredibly cold, but I guess it is completely rational from a payer's financial perspective.
It is the reality of healthcare economics.
Yeah.
However, the counter-argument from the oncology community is incredibly powerful. Treating a patient with stage 4 metastatic cancer costs hundreds of thousands, sometimes millions of dollars in ICU stays and experimental drugs.
It's astronomically expensive.
But treating a stage I cancer might just be a single, simple outpatient surgery. If we can use liquid biopsies to shift the bulk of national cancer diagnoses from stage 4 back to stage 1, the long-term economic savings for the entire healthcare system are almost incalculable.
So it's basically asking the insurance companies to make a large upfront investment for massive long-term savings.
Exactly. But as we all know, the modern healthcare system often has a very hard time thinking long-term.
Yeah, that is definitely true. Then there's the issue of access. Right now, this all feels like very elite, high-tier medicine. If you're wealthy or you're being treated at a major research cancer center in New York or London, you might get this. But if you're at a small rural clinic, probably not.
That is what we call the democratization challenge. We absolutely have to figure out how to move this cutting-edge technology out of these giant, centralized mega labs and bring it directly to the point of care.
Point of care, is that where the lab-on-a-chip concept comes in?
Yes, exactly. Engineers are currently developing microfluidic devices. Imagine a little plastic chip, roughly the size of a standard credit card.
Okay.
The goal is that a doctor can take a simple finger prick of blood, put the drop onto this cheap, disposable chip, and a small desktop machine can instantly detect dangerous exosomes or specific ctDNA mutations right there in the office.
No courier trucks in the sun.
Right. If we can successfully engineer that and get that cheap technology distributed into local community clinics or low-resource settings around the world, that is the moment we truly revolutionize global health equity.
That is the dream. And finally, let's look at the ethics. We touched on the psychological burden of the patient in waiting earlier, but there's also the massive data privacy aspect to all of this.
Multi-omics data is the ultimate, absolute, personal identifier. Think about it. It's your entire DNA sequence. It's your current metabolism. It's your specific immune response. It is your complete biological identity digitized into a file.
So whoever owns that file knows everything about your physical future.
Right. What happens if a healthy 30-year-old takes an MCED screening test for a life insurance policy, and the test finds a faint molecular signal of cancer, but the MRI shows no visible tumor yet?
Can they be legally denied that life insurance?
That is the terrifying question. Pre-existing condition takes on a completely new dystopian meaning when the condition is just a statistical probability written in your genetic code.
That is a genuinely terrifying thought.
It is, which is why we desperately need robust international legislation to protect genetic privacy before this technology becomes ubiquitous. And as a medical community, we need to completely redefine what the annual medical checkup actually looks like.
Right, because I can easily imagine a future, maybe just 5 or 10 years from now, where I go in for my standard annual physical, the nurse checks my blood pressure, checks my cholesterol, tests my blood sugar, and then the doctor just casually says, okay, let's run your annual liquid biopsy cancer panel.
That is exactly the future we are rapidly heading toward. But we need to build the roadmap first. How do primary care doctors, who aren't specialized oncologists, handle a positive molecular result when the physical MRI scan shows absolutely nothing?
They wouldn't know what to do.
We need entirely new medical guidelines, new training, and new ethics protocols for this molecular phase of medicine. Like the saying goes, we are actively building the airplane while we're flying it.
It's incredibly exciting. It's honestly a little bit terrifying in its implications, but ultimately it is deeply hopeful. The simple idea that we can finally catch this horrific disease before it becomes an unstoppable monster it's the absolute dream we've all had for decades.
It really is. It represents the profound shift from fighting a desperate war to simply keeping the peace within our own bodies.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us on Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.